Hi everyone, I'm Pranav, and today we'll be talking about Boolean algebra. This is basically like an introductory topic in discrete math, like maybe not specifically discrete math, but this is where I encountered it, like when I was doing reading group in discrete math. So I'll just go with that. Okay, so what is Boolean? So for people who have done coding, they know that Boolean means like these are kind of data type, I think, which has value either true or false. In math, we just say that true is 1 and false is 0. So a Boolean is basically a bit. A bit is like, uh, so a bit is something with which you can assign value 1 or 0. It holds like two pieces of information, like either 1 or either 0. So our lecture will be mainly focused on this thing. So we'll first start with a few definitions. Just a second. Let me pull up the definition which I have to go. Yeah. So the first is proposition.
One
Uh,
sec. Why is a bit carrying two pieces of information rather than one? Because it's either one or zero.
oh yeah, okay. I meant like it can take two data types. Sorry, two numbers. Yeah, the amount of information is one. Yeah, you can say it one. Like it either exists or it does not exist. Fair enough.
Yes.
Info is one, but uh number of data points which it can take is two. Yeah, that is what I mean. Sorry. Yeah. So proposition. This is basically a statement. It can be an English statement or a mathematical statement. It just needs to be a statement with which you can assign a truth value. So, like a statement which is either true or false is a proposition. It need not like it cannot be the case that okay, this statement is 40% true. Like if there's something like that, like if there's uncertainty in how truth it is, then it is not a proposition. So like something like it rained today, this is a proposition because you can say it with certainty. Like either it did rain today or it did not rain today. It's not like, but if you consider like it might rain today, then this is not a proposition because it is not certain. It's like something like 1 is not equals to 2 is a valid proposition. Okay. So we usually denote propositions by like letter P or Q or R, like these letters. And so P can have value true or false, or you can say 1 or 0. So now we have some operators which are called bitwise operators. These are just functions basically, which work on, you can either say bits or truth value. So once I define what bitwise operators are, like some example, it will be more clear. So let's just talk about the first operator, which is and. So P is a proposition and Q is another proposition. Then P and Q is given the value true if P and Q both are true. So if you draw truth table is basically like you take all the proposition and take all the possible combinations of their truth values and you see what the function gives you. So this is a truth table for and function. So you consider all the possible combinations. So like it can be true, 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 false, false, true, false, false. So how is the and function defined? It is true if and only if P and Q are both true. So in this case, this is true, but the other cases it is false. So this is how we define the and function. And we denote the and function by this. So like P and Q is written as P and this thing. It's called as and only. It's just notation. So P and Q, we denote it by this way. Okay. So what is AND function and what is the truth table, and like how do you get the truth table of AND function? Are these things clear? If you have any doubt, feel free to ask.
Wait, is the unit like the notation, the intersection symbol?
No, this is not intersection. Intersection is like
It's
inverted U,
like the
right?
exponent
But this is like
symbol.
a pointed arrow.
Oh, okay.
Yeah. Is that clear?
Yeah.
Okay. I assume you do not have any question. There's a message. Okay. Uh, so we have done first bitwise operator. Also, it is called bitwise operator. Okay, I'll cover that part later. Uh, what was covered before propositions? Nothing as such. Like propositions was the first thing that I defined in the class. Yes, Siddharth, if you have a question.
Also, after and there is or and not operators, right?
Yeah, I'm doing those. Have patience.
Oh, okay, sir.
So the second bitwise operator is called OR. Uh, so P or Q is true if at least one of P or Q is true. So P, Q, and we denote P or Q by P and this down arrow Q. And this is the truth table basically. So if true, 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 false, still true, false, true, true, because at least one of them is still true. But when both of them are false, this is false. Okay. Uh, we are basically discussing bitwise operators and what is a proposition. Like bitwise operators on propositions. So like a proposition is a statement with which you can assign a truth value, true or false. And then there are some functions on those propositions, like P, Q, R are usually used to denote propositions. So P and Q is a function on the propositions. P or Q is another function. And yeah, so these are bitwise operators, or you can say functions. So we are just defining those. So I'm defining the OR function here. So P or Q is true if at least one of P or Q is true. And this is a truth table for OR. Another function is the negation function or the negation operator. This is usually denoted by this way, or you can use this, or maybe there are some other notation, but I'm not really like, I don't really remember on top of my head. So, like in all the other functions, you needed two propositions, right? Like it uses two propositions to work. But negation one, it is not tried to call it a bitwise operator, I would say, because it does not work on two bits, but like two different propositions, but it just works on a single one. So it's like negation P, you can say. So if P is true, then negation P is false. Like it just inverts the truth value of that. So the truth table is something like P negation P. And if this is true, then this is false. If this is false, then this is true. So are these three basic bitwise operators clear? Like we discussed and, or, and negation.
Yes, sir. They are all clear.
Okay, other people?
Yeah,
I
it's
got
good.
yes from you. Okay, that's good. Then there's another operator called XOR. We have to yeah. Or this is also called as exclusive OR.
So XOR is like or, but if both are true, sorry, if both are false, then the thing is true. Oh no.
No, so I'll define it.
Oh,
So
oh yeah, both
yeah,
are true and then it is false. Oh yeah.
yeah. So the symbol for this is plus with a circle around it. So P XOR Q is true if and only if exactly one of P and Q is true. So you can denote this by PQ. I'm drawing the truth table now. TT false because yeah, go on. Okay. Um, now am I audible?
Yeah, I think you broke.
Yeah.
Okay. Yeah. Okay. So true true is false, true false is true, and false true is true, but false false is false. So this is how we define XOR. And okay, we probably do not need to define this, but so I'll just quickly go over it once. We do not need this for the lecture in like after that. P implies Q and P if and only if Q. Uh, is there some specific reason for naming it exclusive or? I think the only reason is like you are excluding this case, like when both are true. So that is why it's named exclusive or. But there can be another reason. I'm not really like aware of that. Like exclusive or is like I read it only at one place. I usually call it XOR only. That's where what I had heard it as. So yeah, I'll just draw truth table of these things. Or okay, you can draw the truth table. I'll just tell what the functions are. So P implies Q is if P is true, then Q is true. Or you can try to draw a truth table, and like if you want to, I can check it like later. But this is not going to be useful for the lecture. And P if and only if Q. So you can imagine this as like P implies Q and Q implies P. So P is true if Q is true, and P is false if Q is false, and the other way around as well.
By the way, like this implies and if and only thing, these are not bitwise operators, are they?
I'm not sure if they're called bitwise operators. Probably they are not. Like
Okay.
these are just functions and propositions right now. I think the only bitwise operators you have is like AND or XOR, or probably like NAND and NOR, right? So yeah, like semantically, yeah, they're not called bitwise operators, but it does not really matter like what the language is for now. Like we just have to get the crux of it. So I mean,
Yeah.
if you want to be very specific, you can look it up on
Yeah.
Wikipedia that which ones are bitwise operators, but it does not matter for the lecture.
Uh,
Yeah.
Wait, did
But
we?
as
The
yeah,
implies and equivalent symbol is, I think. Can you scroll up a bit?
yeah.
Yeah, he wrote P arrow Q when and he gave the condition for that as the equivalent. Isn't that the opposite?
No, no. For P implies Q, this is the condition,
Oh, oh, right.
and the other part is
Yes.
yeah.
Yeah.
Sorry, that was a little messy, but yeah, and also for that, I think only these are bitwise operators. So yeah, NAND for not and similar for yes. Okay, so this was just the definitions. Like I hope the operators are clear. Uh, here's a quick question. Mm, Explain without using a truth table that I'll just write the expression once. Q or negation and R or negation P. So like this is true when P, Q, and R have the same truth value.
Sir, what do we need to find?
You have to prove that this thing this expression is true if and only if P, Q, and R have the same truth value, and this is false otherwise. This is the question.
So only if P, Q, and R have the same truth value, the entire expression is true.
Yeah, you have to
Okay.
prove that. And you do not, you cannot use a truth table. Like you can like P, Q, R, and then make 8 cases without using that.
Sir, this is very easy.
Okay.
P or not Q, but the thing with my proof is this involves Frege formula. P or not Q is equivalent to P implies Q. If we use that, it's very easy because then you get P implies Q, Q implies R, and R implies P are all true. And that the only way for that to happen is for the entire cycle to have the same truth value. Because otherwise, if one of them is different, at least one of the following statements should be false, and we are done.
Yeah. Okay. That works.
That's the easiest way of proving it. At
I
least
think you
that
can.
that's
yeah, I
what
mean,
I
like,
found.
yeah, I get your proof, but I think you can probably do it without using this as well. But yeah, the proof I had in mind is like sort of similar to truth table without using that truth table. But yeah, this is a better proof. So okay, so for people who did not understand it, I'll just go over this proof and then I'll go over the proof that I had. And feel free to share if you have any other ideas as well. So it says that P implies Q, like this is expression one, let's say, and another is P or not Q. Both of them are equivalent. So for two expressions to be equivalent, it means that they have the same truth values given a particular truth values of P and Q. So like if they have the same truth table, then the two expressions will be equivalent. So we can check. So PQ, P implies Q. So the truth table is true.
So that way P implies Q is a bitwise operator.
Sure. Yeah, as I said, I'm not really sure of the semantics. Yeah, I mean, it is a combination of bitwise operators. So yeah, it should be.
Yeah, like because you can assign a value of true or false to it. So
Yeah.
that's the definition. Yes.
Oh, okay, fine. Yeah. And negation Q will be. I'm just drawing a truth table by the way, for people who it's not clear. And P or negation Q. So true. Wait, no. If P then Q. What you said is not true, right? Like in this case, these two things does not match.
Huh? Oh,
P implies.
oh, oh yeah, it's not P or not Q. It's not P or Q. Oh, my proof was wrong. It's not P or Q.
I mean, your proof should also hold in that case, even if that's true, no? Not P or Q. So not P will be false.
Could you show me the thing again?
True, false.
Not.
Just a second. Yeah, okay. Not pure Q works. Yeah,
It's
not pure
not
Q
P or
works.
Q. It's not P or Q.
Yeah, that would work.
It's not P or Q. It's not P or Q. In that case, the proof still holds. The only thing is, it's not. The thing is,
I
you
see the
have to
proof. I
just
see the proof.
yeah, you have to swap the two things. That's all. Instead of P or not
Yeah.
Q, it's not Q or P. That's the only difference. I'm trying to prove it without anything.
Okay. Yeah, so you can see like these two expressions are equivalent, not P or Q. So what you can do is, so this is like not P or R, which means that P implies R and R implies Q and Q implies P. All of these should be true, right? Like all these things should be true. So if let's say one of them is false, like at least P, Q, or R is false. So let's say without loss of generality, P is false. So P is false. So for this thing to be true, Q must be false. And from that, we get that R must also be false for this thing to be true. So if one of them is false, all three should be false. Otherwise, all three should be true. So
Yeah.
that proves the question.
Yeah, I found another proof, sir, which doesn't involve this formula.
Go on.
The proof is this. Take P or not Q, Q or not R, and R or not P. Now, what we need now, let's prove by contradiction. Assume without loss of generality, P is true and Q is false. It's without loss of
Yeah.
generality because we can take anything. If P
Yeah,
is true
yeah.
and Q is false, for P or not Q to be equivalent to Q or not R, then you have to have R should be false.
Hey, what did you say?
You
For
know,
P or not Q?
we need P or not Q to should be equivalent to Q or not R, and it should be and both should be true.
Why do you want this equivalence?
Huh?
You do not want the equivalence here, right? Like you want both of them to be true.
I mean, both are true. Not equivalence. Both are true. Now, if for Q or not R to be true, for Q or not R to be true, Q is false. So not R has to be true, which gives R is false.
Yeah.
But if you consider R or not P, then you get not P is false. So then you have to have R equal. If R or not P, for that to be true, then you have to have R equals true.
Yeah.
And
Yeah,
R
that is the proof
cannot
that
be
I
true
had
or
in mind.
false at the same time. So we're done.
Yeah. Okay. Is that proof clear to everyone, or should I go over it again? Yes or no would be helpful. Okay.
It's
So
fine
I
for
assume
me.
that's clear. Yeah. What was the next thing? Okay, yeah. There was another question that a friend told me today. I'll give it as a homework. I'll not do it in class. Like you can try it later. So you have an array of 2n plus 1 numbers where exactly n numbers appear twice in the array, and exactly one number appears once. Find an algorithm let's call this exactly once number as k, to find k in O of n. For people who know time complexity, yeah. But essentially what it means is like you have to find k in some like Cn plus d number of moves, where C and D are fixed for any given n. An
Uh,
example of such array can be 1, 1, 2.
what are we allowed to do in the algorithm?
Anything. I
Like,
mean, just not go over it manually, obviously, because that will take more than n time. Because you have to check that it like this number. So like you pick this number 1 and you check over the other remaining numbers. Also, this array is not ordered. So you cannot do a binary search as well unless you order it yourself. So like the thing you're allowed to do is like essentially anything, like any operation you want. You just have to find an algorithm. Is the question clear now?
Yes, sir.
Wait,
Yes.
do we ask each number what, whether it, I don't really exactly get it.
Like,
We're
are
allowed
you
to do any,
supposed to
Like,
ask a number or do you appear twice?
no, not that way. Like, how do I give an example? So an algorithm is basically a set of moves which you can do. It's not like Alice and Bob is there and you are asking Bob. It's like, Tower of Hanoi, right? Like, you have three
yeah.
sticks and there are like something here. So like the algorithm to put this into this stick will be like, you take first step and you put this here. You take second step and put this here, and take third step, put it back here. So this is an algorithm of 3 steps. So you have to find an algorithm which takes like less than equals to Cn plus D steps. Like the number of steps taken is like linear. Is that clear now?
Yeah, so we can basically check out any index and tell what number is there at that index, right?
Yes, but that will take, yeah, that takes a constant time. Yes, you can do that. Okay. So I'll not discuss this problem much right now. You can discuss it over with me over DM later if you want. So let's move on. Uh, okay, I had to
But
do a
sir, could
question,
you
but
give
I'll
us a small hint in how to in the method to solve this?
not right now. Try it for enough time, and then if you're not done, then you can ask me over DM.
Oh, okay.
Yep. So we'll go over a few more notations. Uh, one is this notation, and you might want to mute. Okay. So and pi goes from 1 to k. This is basically like the same as summation. It's like you take and of the k statements, p1 and p2 and p3, so on till pk. And another is or from I equals to 1 to k is just p1 or p2 or p3 pk. So this was just two notations. Okay. Next we talk about satisfiability. Satisfiability. So you have a bunch of expressions. Uh, is that called expression? Yeah, okay, I'll call it expression for now. So like an expression can be like P or Q. So like this is one expression. So like you have a bunch of expressions. Let's say you have like some n expressions in free variables. Like an example of this can be P or Q. Uh, or let's say Q and R, P or Q and R. So like these are three variables, right? Like P, Q, and R are the variables involved in these three expressions. So this set of statements is called satisfiable if there exists a certain assignment of truth values to PQR such that all the expressions are true. So is the definition of satisfiability clear?
Yeah.
Yes, sir.
Okay. Yeah. So now let's move on to the interesting thing now. Question. Find the set of satisfiable conditions for a Sudoku. Let me explain the question, or like what it means basically. So I hope everyone knows a Sudoku. Is there anyone who does not know what a Sudoku is?
Sir, just to be clear, a Sudoku is
Yeah.
basically like a 9x9 grid where we have to fill the numbers 1 to 9 such that in each row, column, and 3x3 blocks, 1 through 9 should appear exactly once.
Yeah. Yeah. For those of you who do not know,
That
he
includes
just stated the
3x3
definition.
blocks, right?
Yes, it does.
Why did I just say blocks?
Wait, every column and every row should have all the 9 digits.
Yes. And each of the 3x3 blocks should have all the 9 digits, which means that there cannot be repetition in a row or a column or in a block.
So the problem essentially means like, wait, so all Sudoku are not solvable.
No, I mean, like when you say Sudoku, it's like you're given some number and you are supposed to fill the other numbers. So, yeah, but what here we are trying to do is, let's say, we are given certain numbers, like we are given certain filled numbers in the cells. I do not really want to draw Sudoku nicely. Okay, so suppose we are given some numbers here. Let's say a 5 is given here, 5 is given here, and a 5 is given here. That is all you are given. And you have to find a set of conditions such that when you put it in a program, it will return you all such possible Sudokus with 5s being placed here. Sudoku has like all the possible 9x9 grids, satisfying all the conditions which a Sudoku does satisfy. So, is the question now clear?
Yes,
Yeah, and also someone is asking.
Yeah, I saw that. I'll tell that. I'll Dipanshu, I'll answer your question in 2 minutes. I'll just go over this once. So I'll just give you what I mean by set of satisfiable conditions. So like okay, or rather think about it for 2 or 3 minutes and like tell me any ideas you have. Yeah, just think about this problem. Meanwhile, Dipanshu, I'll go over satisfiable condition. So I'm assuming you know what a propositional variable is and what are and or functions. Because if not, then that'll take too long to go over again. Do you know what is a preposition and what are like and function or function? Bitwise and bitwise or.
what functions?
No, like bitwise and bitwise or, which so like P
I,
and Q. Uh,
I know set
like
theory it is like 11, 12.
what did you say?
I know basic like set theory of 11, 12.
No, not that. Like this. Do you know what is a proposition and what is this P and Q, which I have written here?
No, not
Okay,
exactly.
it'll probably take too much time and I don't want to go off topic.
Yes, sir.
So
No
it'll be better
problem.
if you can see the recording later. Sorry.
No problem. Can you just tell the topic name, what P and Q?
Oh, I'm discussing about Boolean algebra, like proposition and yeah, just Boolean algebra. If you search Boolean algebra, you'll get more information about that.
Thank you, Bhaiya.
Yeah, no problem. Yeah, so any ideas with this problem? We can use three numbers, row and column and box of 10 bits and set ith bit to check if it is present or not.
Huh? What did you say, sir?
I'm just reading the chat message. Yeah, I think you're along the correct lines. Like, I'm not really sure about the English, like if I'm understanding correct, but you're probably saying correct thing. So what I think he's trying to say is we assign uh let's say we consider this cell. So we can label these cells like, so let's say this is row number 1, this is row 2, row 3, row 4. We label all the rows from 1 to 9 and we label all the columns from 1 to 9. Then uh we can define the propositional variable pi comma j comma n as the proposition which is true if the number n is in block I comma j. I think this is what Shivang meant. I hope so. Yeah. So is it clear how we are defining the propositions? Yes, nice. So let's say we know
So
that there's a 5
you
here, right?
essentially want,
Yeah.
I mean, like you are basically labeling those blocks false, which don't have a given number already, right?
No, we'll also code it up for the other blocks, because when we see the final set of conditions, we'll need that. So like in this case, we'll just have, so like let's consider this block. We already know that there's a 5 in there, right? And this is block 5 comma 5. So
Yes.
P5 comma 5 comma 5 is true because 5 is in that cell, but something like P5 comma 5 comma 1 will be false. Is that clear?
Okay, fine. Yes.
Yep. So that is how we are defining the propositional variables. So now let's try to think what a Sudoku has conditions. Like, let's think about the first condition. It says each row must have exactly all the numbers from 1 to 9, right? Which means that there cannot be a repetition of numbers in the row. Like if 1 is there in the row, then 1 can be there at exactly one place, right? So
Yes.
let's try to think of uh, this condition. Like how can we write this condition? Row 1 has exactly one of 1, 2, 3, so until 9. So this is basically like saying, so I go over all the columns in row 1 by 1. Uh, 1 second. Okay, so what I can do for this is, in row 1 particularly, okay, I'll just draw it here. Let's say this is our row 1. 1, 2, 3, 4, 5, 6, 7, 8, 9. This is row 1. I'll go over each cell individually. P1 comma J comma 1 true only for one time. Yes, exactly. That's the idea. So I'll go over each cell one by one and I'll check for the number 1. I want that 1 is there in exactly one of these cells. Right? 1 is there in exactly. Yep. So I wanted 1 is there in exactly one of these cells. And then I'll check for 2. And I want that 2 is there in exactly one of these cells. So until 9. But notice that we can loosen this condition a bit. So if we have that 1 is in row 1 at least one time, 2 is in row 1 at least one time, so
Yes.
until 9 is in row 1 at least one time. If all of these conditions are true, then notice that this automatically implies that all of the numbers are in this row exactly one time. Because imagine that 1 is like, let's say, 2 times in this row, and the other numbers are at least one times, right? Which means there must be at least 2 plus 8, which is at least 10 cells in the row, which is not possible. So if this set of conditions is true, this automatically implies that there's like all these numbers are exactly ones. Okay. So now how do we check this? Let's think about this condition individually now. So we just want that P1 comma P1 comma J comma 1 from, we can take or J equals to 1 to 9 is true. Is this clear that why do we want this to be true, for this condition to be true?
Yes.
Like this thing is just P1 comma 1 comma 1 or P1 comma 2 comma 1. So until P1 comma 9 comma 1. Is this clear? Like this will be true if at least one of these things is true, which will mean at least like 1 is there in at least one of these cells. So that is clear, right?
So I actually have a bit of a confusion regarding the representation of 1 comma j comma 1. Please
Yeah,
clarify.
go on. Okay.
Um,
So see, we define the proposition I comma j comma n. So like, you know what is the proposition, right? It either has true or
yeah,
false value.
yes, sir.
So I say this proposition is true if the cell I comma j has number n. So we consider this cell. Okay, let's consider this here. Suppose I place 9 here. So 9 is there in the cell 1 comma 3, right?
Mhm.
Which means P1 comma 3 comma 9 is true.
Okay, sir, understood.
Is this clear?
Yes, sir. Thank you.
But P1 comma 3 comma 7, this will be false, right? Because 9 is already there.
Mm.
Is that clear?
Yes, yes, sir. Thank you.
Cool. Yeah. So I hope this is clear. This means that 1 is there in row 1, at least once. And now we have to check for all the numbers from 1 to 9. So what we can do is, so we want that this is true. We want that this is also true. And we want this for all the 9 numbers. So we can just consider this. And I goes, sorry, n goes from 1 to 9, or j goes from 1 to 9, p1 comma j comma n. Is this clear? That this will ensure that row 1 has all the numbers from 1 to n.
Like this has to be true, right?
Yes, this has to be true. Like if this is true, then row 1 has numbers from 1 to 9.
Yeah.
And we have to do this for all the rows. Like this should be true for row 1, and then we should have this also. N goes from 1 to 9, j goes from 1 to 9.
So we can
P
take the
2
and.
yes, exactly. So and I goes from 1 to 9, n goes from 1 to 9, and or j goes from 1 to 9, p of I comma j comma n. We want this to be true for the row condition. Is this clear?
Yes, sir.
Okay. Now in your notebooks, you can write column condition. I'll give you a minute for that. And I'll just add it over here and then you can match. So like think about that for a minute. And in the meanwhile, I have to check something. I'll just quickly do that. Yeah. So I hope you all have written out in your notebook. Do you want more time? Okay, I assume not. So for columns, we want to go over all the columns one by one. So we take and for columns. Here we have j. And then in each column, we check for each number. So we take and for each number. And we check that each number is in each row. So this will be the condition for columns. Is this clear? Okay, one person said yes.
Yeah,
So, sir,
yes.
I is the x-axis similar to the x-axis.
It's like the rows, labeling for rows, like row 1, row 2, row 3. This is I.
Okay, sir.
Yeah. So is it clear?
Yes, sir.
Okay. So we have these two conditions. Now we also want to make sure that each block, like let's say this block has all the numbers from 1 to 9. So how do we do that? Think about it for a minute. Okay, not a minute, like take 2 or 3 minutes. Take until 7:21. Think about it. And then I'll write it because it's slightly hard to code up the numbering for blocks. If anyone has any idea how we can encode blocks, then let me know.
So can we just divide the I and j into multiples of 3 and separately do it?
Yes, that is along the correct lines. So, okay. So what we do is we label the blocks now as well. Like, so we can call this as block 1, comma 1. This is block 1, comma 2, block 1, comma 3, 2, comma 1, so on. And we can use R, comma S for denoting the block number. So basically what we are doing is we go over all the blocks from 1 to 3, and we go over all the blocks, and in each block we check for all the numbers, and okay, yeah, so in, let's say, block 1, comma 1, the rows range from row 1, you'll see row 2, you'll see row 3, and you'll see column 1, column 2, column 3. So it's basically you're going over column from I equals to 3R minus 1 plus uh, oh, okay, sorry. Better way to do this is rather. You go like each block has 3 rows and 3 columns. So you go I equals to 1 to I equals to 3, and I equals to, sorry, j equals to 1 to j equals to 3. P of, and yeah, so the row number ranges from 3 times R minus 1 plus I. So if you see like block 1, this will range from like R is 1 in block 1, right? So this will range from I equals to 1 to 3. If you see block 2, comma 1, which has row 4, row 5, row 6, and column 1 to 3, then this will be like 3 times 2 minus 1 plus I, which is 3 plus I. So this ranges from 4 to 6 as required. So P of 3R minus 1 plus I, comma, similarly we get 3S minus 1 plus J, comma, N. It's slightly, oh, yeah, it's slightly hard to get the hang of it in the first go, but once you like try it yourself manually, you'll see that why do we want this condition. Does everyone get this though, like intuitively, that why do you want this?
Yes,
Yeah, other people?
It's actually starting to make sense now, sir.
Okay, I assume it's clear to other people, or if not, then please ask. Okay, so these are the 3 conditions that we wanted, right? But there's one more slight, like, technical condition which everyone skips usually, that each cell must have exactly one element, right? That is a necessary condition.
I got not
Like if
required.
one cell has 2 elements, what?
I think not required. We in the conditions it already is there.
See, you manually know that you cannot put 2 elements in a cell, but if you code this up in a computer, he does not know that he cannot put uh 2 numbers in a cell. Like you have to specify that in each cell exactly one number goes, right?
Oh yes.
Yeah.
And that 5 condition is also left.
Which condition?
The
Oh,
5.
okay. No, I'll go over that. That condition, yeah, I'll go over that in the end. Yeah. So for now, the condition is each cell has exactly one number, which means that let's fix I and j to, let's say, 1, comma 1 for now. So if P1, 1, let's say sum n is true, this implies P1, 1, n dash is false for all n dash not equals to n,
Yes, sir.
right? So we can say something like P I comma j comma n implies not P I comma j comma n dash. And we can do this for let's see how to write the numberings. So obviously we do like and I goes from 1 to 9, like all the rows and all the columns. And then for each row and column, we take for and n equals to 1 to 9. And n dash equals to 1 to 9, but you also had a condition that n dash is not equals to n. So this is how you can code up this condition. So is this clear? But
Yes.
doesn't a computer... Okay, nice. Doesn't a computer allocate a fixed space for only one to one? Yeah, I mean, you're defining it that way, right? Like okay, you're thinking about high level programming languages. Like we are not thinking about basically programming. We're just assuming that, okay, forget computers. I think like you're giving instructions to a baby who just understands this language of propositions. So you need to specify that each cell must have exactly one element. That's the point. Like, suppose you're coding this up in Python. Yeah, sure. You do not need this condition because once you create a grid, you know that it will only take like one element for a cell, or otherwise it will overwrite. But that is coded in the background, right? Like that is how the grid is created or something. Like maybe for a very low level language, there's nothing a thing called like overwriting. It's like adding the stuff, like instead of overwriting the stuff. So that is what I meant.
So, and I'm also having a bit of a trouble with the notations here. So
Okay.
if all the P, I, J, N and the conditions on the left hand side satisfy, so what does it mean, sir? Does it mean like,
Sorry, can you repeat your question?
so suppose all the conditions on the left hand side are true, then does it mean
Left hand side as in
before
this?
the implies arrow, sir? Before the uh, if LHS is true, then RHS is true.
Yeah.
Sir. So if the left side is true, then what does it mean for the right side, sir? Does it mean that P of I, comma J, comma N dash exists, or
Oh,
does it?
oh, oh. Okay, yeah, I did not specify on the implies. I thought we won't need. So this function, what it means is like P implies Q. This is what it implies. This means that if P is true,
As a Q is also true.
then Q is also true.
So
But
suppose,
if P is false, then Q can be true or false. We do not really care. So this
oh,
is whole one condition. Like once you have I, J, and N dash fixed for some numbers,
okay,
it
sir.
says that if this is true, which means if the particular cell I comma J has the number N,
Yes, sir.
then this implies that not having number N dash in I comma J should be true, which means
Okay,
not having N dash means N dash cannot be in the I comma J cell. This is what this condition means.
okay, sir. Yes. Thank you.
And this is just iterating over all the numbers, nothing else.
Ah, thank you, sir.
Okay. So yeah, these were the conditions. Yeah, someone said we left this condition, like 5 is in this cell. So what we do is like once we have coded up all these conditions, like we have it's like we range from I goes from 1 to 9, J goes from 1 to 9, and N goes from 1 to 9, and you have P, I, comma J, comma N can take true or false value. So like you test over all these values. So like what you do is in one test case, you assign like some particular truth values to all these propositional variables. Like there will be exactly 729 such propositional variables, right? Like 9 times 9 times 9. There's 729 variables. You assign true or false to all these variables, and you see if all these conditions, condition 1, condition 2, condition 3, condition 4 are satisfied. If they are satisfied, then that is a satisfiable solution to Sudoku. But you had that this cell has 5 here, right? So what you can do is when you're assigning these variables truth values, instead of varying the truth value of this thing, you can just say that this is true forever, and these things will be false forever. Like you're basically just reducing the number of assignments. Does that make sense, or should I rephrase that?
So can I just retrace that from the P of S comma S comma S?
Okay. So basically, like when you see a Sudoku, there are some numbers filled in the Sudoku and you have to fill the remaining numbers, right? So
Yes, sir.
let's say, okay, so okay, before that, let's take one step before. What is the point of these conditions? Like we found 4 conditions. Let's say C1, C2, C3, C4. What are the point of these 4 conditions? So
So,
like,
so, okay.
yeah.
So when we see a solution for the particular condition already filled out, we know that we can derive some other impossible cases.
Okay, I'm not really sure what you mean, but I'll just say it myself. It's slightly long time.
Yes, sir.
So it's like you have 729 propositional variables of the form P, I, J, N, right?
Yes, sir.
So we assign some truth values to all these variables. Like let's say we assign 300 of them as true and the remaining 429 as false. And now for those truth values of these variables, we check, okay, is condition 1 satisfies? Is condition 2 satisfied? Like, are these 4 conditions satisfied? If all of these 4 conditions are satisfied, which means that assignment of truth variables to these is a solution to the Sudoku. And if you know solution, we can fill the Sudoku, right?
Yes, sir. Now I can
But we are
understand.
assigning it ourselves. Like it can be like some particular, like let's say P1, 2, 1. This can be true or false as per our will. We are checking over all such iterations. But once you're given that, okay, some particular cell, let's say 3, 4, has value 9. What we can do is we can reduce our work and like we can just assign 3, 4, 9 as true. Like we do not need to check the false case because this value already has 9, this block. We know that from before. Like this is what we can do. And we can just iterate the other things. So like let's say we know that 10
Yeah,
squares
yeah.
are filled.
Eliminating the other possibilities, sir.
What did you say?
So basically, by getting a value already given in the Sudoku, we're eliminating the other possibilities.
Yes. Like we
Okay.
are eliminating the possibilities related to that square
Okay.
of checking. Yeah. Okay. So is Sudoku clear to everyone?
Yes, sir.
Okay, I see one yes.
Yes, bro.
Yeah, it's clear.
Okay. Okay, nice. 3 people said yes, which is good. Okay, I had to do a n queens problem after this, but I don't think we'll have time for K maps after that. Okay. 1 second. Will we have time for K? Okay, so see, there are 2 options we can do right now. We can discuss more on this idea which we did for Sudoku, and we discuss n queens. How do we make sure that we only have a unique solution? Okay, so that is not always possible. Like the Sudokus you see in newspaper do have a unique solution. Like you know that from before. But let's say I give you a Sudoku where I only fill this element as 5 and the other all the blanks are empty. You do not know that there exists a unique solution. Like there obviously does not. There are like a lot of ways to fill this Sudoku, right? So the what we did just gives you all the possible solutions to given Sudoku. Does that answer your question, Sahil?
So one doubt.
Cool. Yeah.
How can we set the conditions that the number of, like, there are many solutions. So how can we set conditions that there are like 3 solutions or 1 solution or no solution or n solution or
Okay. So Uh, I do not see a condition for that in propositional logic as such. But if you're talking about coding, what you can do is like once you have coded up all these conditions, you go over all the possibilities of propositional variables and you can create a variable number of solutions. And once you find one solution, you can append one to this. Like, okay, I found one solution for this particular values, so I add one. And now I continue my variation of the propositional variables. Okay, I found another solution, I add one. So you can essentially count the number of solutions you have at the end as well. And that is exactly what you want to do, right?
Can't we like in the starting set conditions that only two solutions we will get in and some conditions?
Yeah, sure. I mean, what you can like, okay, that comes to the coding part. I do not want to get into that. But like what you can do is like you can set a while loop. Like while the number of solutions is less than two, you keep on going. And as soon as it hits two, you just stop. So you'll get the two solutions.
Okay.
Yeah. Yes. So someone said we can add more fixed values from the chosen solutions into our Sudoku and we have a unique solution, right? Yes, eventually you'll have a unique solution with a large enough, like large number of values filled. Okay. Okay. So there are two things which you can do right now. We can discuss n queens problem, which is related to Sudoku, like like ideas and all. We can discuss that. We can discuss Chomp. It is a game which is not related to this thing, but it's just one thing. So I included it. And we can discuss another problem related. It's just a fun problem. And uh, and I can define what a Boolean function is. Directly define. Or we can cut all this part and define what a Boolean function is and go over some more definitions and then see what a K-map is. But the thing is, I'm not sure if we'll get time for K-map. So like it's possible that we just end up defining the things and not do fun thing. So and also if we decide to go over this, I might take another class for K-maps. So what do you want to do? Okay, it's one person with more problems. Okay, problems. Cool. Okay, we'll first do. Okay, let's just do queen problems because we will learn flow with that. In queen's problem. It's just the problem just says that find the set of satisfiable conditions, just like we did for Sudoku. Satisfiable conditions to place 8 queens on an 8x8 chessboard such that no two queens attack each other. So a queen can attack like
So, but isn't this actually manually possible without the use of computers? Uh, Using a bit of combinatorics as well as probability.
huh? I mean
Majorly,
for 8, sure, but what if I give you a 16x16 board? It's
then
just
that
too
will
much to
be,
do it manually, right?
yes.
Yeah. So that is why it's called n queens problem because you can generalize that thing to n.
Ah,
But we'll just do it for 8. The idea is same.
okay.
Yeah. So a queen basically attacks row wise, column wise, or diagonally. So yeah, you have to place 8 queens such that no two attack each other.
So I think if you go around rows or columns, it would be easier. But and for the diagonal part, you are trying to find if you can form a certain square root.
Uh, for what did you say about the diagonal thing?
Like you have to for like if the two queens are in a diagonal, then there is a square existing, right? And if they are not, then it is a rectangle. If like in
Ah,
real.
that is a good idea. I did not have that in mind. Let's see if we can. Yeah, but how do
Like
you convert that like idea? Like, how do you use that idea? I mean, mathematically, you can like literally code up a diagonal, right? Like, let's say you have I comma j cell.
oh, okay,
To code up
yes,
a diagonal,
yeah.
it's just
You
like I
increment
plus
both
one.
of them with +1 or -1.
Yeah,
Okay.
like I can just do I plus one, j plus one, I plus one, j minus one. All these points lie on the diagonal, right?
Yes.
Yeah, so you can do that. The square idea is nice, but I don't see how you can do with that.
Yeah, what will this be?
Yeah. Huh. Okay. Oh. Yeah. So how do we do this? Like, what set of propositional variables will you take? Okay, take 2 or 3 minutes, and then we can start.
Okay, so shall we start like
Go on.
whether the square has a queen or not?
Yeah.
Um,
So in this case, we can just take the propositional variable as p I comma j is true if cell I comma j has a queen, right? So now what are the conditions? Each row,
Robert,
what did you say?
nothing.
Okay. Each row has exactly one queen. Okay, why is this true? This is true by PHP because then if it is present, then making sure that there's no other queen which is present on that same. Yes, exactly what I'm saying. So each row should have exactly one queen because if not, then you have 7 rows who place 8 queens. Two of them will be in the same row, and those two will attack each other.
So it's a
Or
Sudoku
we can say
basically
each row
getting
has.
the. So it's
What did you
basically.
say, Rishwan?
So it's a Sudoku in which the 3 by 3 boxes gets converted, compared with diagonals.
Yes,
Okay.
that's the thing. Yeah,
Wait,
and we
what
can
did you
change this
say?
exactly. Oh, it's just like Sudoku, but instead of the 3 by 3 block condition, we have diagonal condition.
Yes.
Yeah. So each row has greater than equals to one queen. And so I'll just write how to code this. And because this is similar to Sudoku. So P I comma J uh, or J goes from 1 to 8. So this is the row condition. Does everyone see that how this holds true? Like we want this to be true, not how it holds true. But like this is true that how it's ensured that each row has exactly one queen. Does everyone get that? It's the same thing as we did in Sudoku, no? People, yes or no would be nice, sir.
This one ensures that every row has only one, right?
Yes.
Yeah.
Okay,
Okay.
that's what.
Would someone like to tell me the condition for columns? Yeah, just reversing them. And j equals to 1 to 8 or I equals to 1 to 8 pi comma j. Okay. And now let's think about the diagonals. So suppose you're on cell I comma j, then your diagonals are this or this. So if
So
you see,
essentially,
yeah, go on.
I mean, I thought like there should exist a case such that if if A comma B and C comma D are on diagonal, then A plus K and B
Yes.
plus K would correspond to C comma D.
Yeah. So like, so there are two diagonals, right? Like one is this one. We can see that if we go one row down, we also go one column right. Similarly, if we go one column up, we are going one column left. So it's basically like if A comma B is on the diagonal, then all the numbers of the form A plus K comma B plus K, K can be negative as well, will correspond to the things on this diagonal, right? Like let's say this is 3 comma 3, and this is 4 comma 4, this is 5 comma 5, 6 comma 6. So A plus K comma B plus K. But for the other diagonal, the condition is like A comma B. Okay, we see we go one square up, then we go one square right. Or if you go one square down, then we have to go one square left, which means A comma B should be A plus K comma B minus K. Like this is 3 comma 3, but this is 2 comma 4, but this is 1 comma 3, sorry, 1 comma 5, and this is 2 comma 4. We end in around 15 minutes. And this is 1 comma 5, right? So once we are on the diagonal, like let's say we are on the square I comma j. Uh, Hold up. I think there's a better way to do this. Oh, we can just check each diagonal manually, right? Yeah. How many diagonals will be there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yeah. Okay. So we can just check each diagonal. Oh, can you just show the second diagonal? Okay. This is the second diagonal, the purple one. So see,
That would
if
be.
you're in 3 comma, oh yeah, go on.
So, but a queen can
No, I
possibly
wanted
go in
to.
two diagonals. Then
Yeah, queen attacks on both the diagonals. So you have to check for both the diagonals.
okay.
Like checking diagonals
Again,
manually would be a little inefficient. Right?
okay. What is the other way then you can do it?
No, like manually, as in like you are when you are actually counting.
No, I mean like just go over each diagonal is what I meant. Like you go over this diagonal, then you go over this diagonal.
Ah, okay.
Not manually, like
Ah,
coding up. I meant
yes,
manually
yes,
in
yes.
another way. Yeah. Okay, for the other diagonal, if you see you're on 3 comma 3, then this cell is 2 comma 4, 1 comma 5, 2 comma, oh god, I messed up somewhere. Oh sorry, this should be 4 comma 2, 5 comma 1. So if you notice that uh the sum of these squares, like the sum of the coordinates is constant. Like 1 plus 5 is 6, 2 plus 4 is 6, 3 plus 3 is 6. So they're of the form A plus K comma B minus K. So that is the second diagonal. Okay. So now to code this up, what we can do is let's talk about this sort of diagonal, like this directional diagonals. So, uh, hmm, 1 second. Okay, so if you see this thing, I'll have to draw this again. Kya? So we can like the diagonals of this direction, we can see them in this format, like in a different color, maybe like yeah. So like we can see this as like one diagonal, like from this cell, and then there's one diagonal from this cell, one from this cell, and you go on downwards, and then one from this cell this way. So basically, like there's a diagonal originating from the top row and the leftmost column. So we can go like, let's just go over the leftmost column once first. So and I equals to 1 to 8. And how do you code up the diagonals? So you want each diagonal to have exactly one plane. Okay, you don't want each diagonal to have exactly one plane, but at most one plane. So negation of that will be okay, wait, this is slightly hard. How do you do this?
That's what, as I was saying, when you keep the queen on the edges, that time you are supposed to consider both the diagonals, sir. One going linearly up, one going linearly down.
Yeah, yeah.
So, what mathematical function, what function will we do to, if we solve separately for one diagonal going linearly up and one diagonal linearly down, sir? Then how would we further simplify that?
Yeah. Okay, maybe there's another way to do this. Okay, we can probably do it this way. So if there's a queen on I comma j, then we check the diagonals for I comma j, and there should not be any queen on those two diagonals, right? So the condition for diagonals is, and you go from I goes from uh 1 to 8. So if we are checking diagonals of this form, like we first check diagonals of this form, in this case, the difference is constant, like the difference of these things. So difference of the coordinates, like a minus b is constant, right? So I goes from 1 to 8, and then, oh, sorry. Maybe it's better to take a comma b here. If there's a queen on a comma b, then I goes from 1 to 8, and then b will be equals to, uh, b should be equals to a minus b minus I. Yeah, okay. We need not write this. Listen, I'll just quickly write this and then I'll explain it. I not equals to a, b, I, comma, a minus b minus I. Yeah. So the thing is, we're talking about diagonals of this format. And we see, it's like if a comma b and c comma d are on this diagonal, then a minus b is equals to c minus d. So if there's a queen on a comma b, there shouldn't be any queen on these cells, other cells, right? I goes from, okay, one more thing. Does I goes from 1 to 8 always? Okay, yeah. There shouldn't be any queen on these things. Which means if we take not of this thing, like this means that there shouldn't be any queens. Like and of all these things should be true, right? It's like this is basically like I goes from 1 to 8, I equals to 1 in this case, and then the j coordinate will be, so c is equals to I. Oh, maybe I messed up this. So j will be a minus I, a minus b. Okay, so just minus a plus b. So this is how j is defined, right? So this should be true. Is this part clear? I slightly messed up the explanation, but is this clear now? If not, then I can explain again.
So can we just have like some seconds to process it?
Yeah, sure. There's a slight flaw with this, but that is not a major flaw. But I'll come over it again. I'll come to it. But let's see if this makes sense right now. Okay, just tell the j part again. So see, if a comma b and c comma d are on the same diagonal, then a minus b equals to c minus d. What I'm doing is I'm iterating over all the rows, and I have to check all the elements lying on the diagonal on that row. Like, so I iterate over this row and see only that element which lies on the same diagonal. I go on the second row, but I only care about this square. Third row, I only care about this square here. So, like I know a comma b, like a comma b, I have like these are fixed, and then c is I, like ith row. So d, like find this cell. We put a minus b equals to c minus d. This is the condition we had for the diagonal here, right? From here. So a minus b equals to c minus d. This will give you d equals to c minus a plus b, which is I minus a plus b. That is what I wrote here. So you check the cell p I comma minus a plus b minus I, and you check negation of that. Okay. Is it clear to other people? Yes.
Yes. Yes.
Okay. Rishwan, this is clear to you. Ask for some time.
It's fine, sir. You can go on. I just need some time for reviewing.
Okay. But okay, the slight flaw here, which I was talking about, is suppose you have this cell. The coordinates are like 7 comma 1, and let's say you take I equals to 8 in here. Then this coordinate will be minus 7 plus 1 minus 8, which is minus 14. But this is not defined, like j should be from 1 to 8 only, right? So what do? Like we can just assume that p of I comma j is false if I is not in the range 1 comma 8 or j is not in the range 1 comma 8. If we assume this, then everything is just good. And this is a like valid assumption. We are not altering our things. So we take care of this overflow as well. Is this clear? Other people?
Yes, sir.
Okay. And similarly, we do for other diagonals. The condition for other diagonal is the sum of the coordinates is preserved. So if we have like c equals to I, then we'll get d as a plus b minus I. So we check p I comma j must imply, and I goes from 1 to 8, not of p I comma a plus b minus I. And this whole thing should go from all the cells. Maybe we can replace 2k here. So is this clear?
Yes, brother.
This is just for the other diagonal. Yes or no?
Yeah, it's
Okay, one person said yes. Okay, what is the doubt? The imply part. Okay. So what I'm doing is, I see if the cell I comma j has a queen. This should imply no queen on the two corresponding diagonals, right? Yeah. So that is what I'm doing. So if pi comma j is true, which means that there's a queen on the cell I comma j, then I check all the cells on its diagonal. Like this is one diagonal, the other diagonal was before. This is the other diagonal. So we check that there's no queen there. Yeah, this thing is for one diagonal, and this is for the other diagonal. Do it for both the diagonals. This particular thing is for one diagonal. And this thing is iterating over all the cells in the grid. Is this now clear?
Yes,
Nice.
yes.
Okay. Any other doubts?
No, sir.
Okay.
No,
1 second. Okay. So it's 8 and I do not have much time right now. So I said that we'll do chomp. I'll just state the problem. Oh, I'll send it on OMC server in announcements and the other problem because I have to end it right now. So yeah, in the next class, if I take on discrete math, like if people are interested, we'll go over what I'll just show my maybe.
One doubt.
This is what yeah, go on.
Yes, I am new. Like I first attend today's class. Is it like
Mhm.
we will discuss these like discrete mathematics, coding related mathematics, or Olympiad mathematics? Like,
So
I'm
it's a math club. There will be like all sorts of math lectures, like college or Olympiad. Most of the time there are Olympiad lectures, but sometimes non-Olympiadish. Like you won't really use this stuff in Olympiads,
okay,
and
sir.
not always will have discrete math. Like probably next week next week you'll have an Olympiad lecture as well, most probably. So yeah,
Okay, yeah. So can you mention when there is a discrete mathematics class in the announcement that it will be
I
clear?
announce all the classes, so you can read from there.
Okay, yeah.
Yep. Yeah.
Thank
So in the next class we'll go over uh what is a Boolean function, how to represent them graphically. Uh, like no need to know this stuff. This is like what we'll do in next class. What is a literal? What is a min term? What is disjunctive normal form? Conjunctive normal form? We'll also go over Carnot maps. And there's some another theorem which sounds fancy, but I'm not sure how it works right now. If I feel it's relevant to the class, I'll cover that as well. So yep, that was it for this class. And I'll stop recording.